So to set the perspective, yes, I mean, India has promised that they would move to close to 500 gigawatt of renewable energy generation by 2030, and an estimate is about 2.4 terawatt hours of storage, which basically puts us in business if you are working on energy storage related devices. So that's the premise I wanted to set up. And like I said, this first part of my talk would present the combination of renewable hybrid power systems with energy storage. And finally, what we mostly talk about is whenever we look at a system as a whole, we are interested in the main challenges, which are their cost and having a very high energy or power capabilities, including very long cycle life. It has to be safe and environmentally friendly. So these are the things that we look for in any device, and how do we achieve one or more of it by making trade-offs on the other parts of these devices. So this is the premise I wanted to set. And to start with, the group, my group at IIT Bombay, we work on primarily lithium-ion batteries in terms of performance and degradation analysis. As I mentioned, about 95% of my group does computational or numerical work. There is very little part on experiments that I'll talk about in the next couple of slides. So mostly performance and degradation analysis, building physics-based models, model-based optimal design and optimization, and also looking at advanced battery management systems. We also have collaborate with people trying to work on building battery thermal management systems, and a few projects on sodium ion as well as solid state batteries. Again, we have collaborators who build these batteries. We build models to validate and test and give inputs to that. So this is more of on the battery side. Apart from this, also work on system level integration, which is what we will see today. So the one on the left is basically the figure on the right top. Sorry for this, I don't have a title here. So basically what we try to do is we try to integrate renewable power sources. So let it be solar, PV or wind systems, and we try to integrate them with battery storage systems. There is also some level of modeling power electronics in these power electronic components. Then we try to see how the battery behaves. I mean, my primary training is on battery modeling, so I'm trying to push physics-based models into these long-term simulations. Mostly what we are interested is in like how it performs for one cycle or 10 cycles, but what happens in a real world scenario. So if you tie it to a grid, or if you tie it to a standalone microgrid, what happens to these batteries? So that's something we do in what we call as system level integration for renewables with batteries, and look at their performance and come up with improvements. And of course, we also work on techno-economic analysis of optimal sizing of battery, which is economical, how would it work and stuff like that. Apart from this, also another electrochemical system, since we are working on large scale storage, I believe lithium ion is not still a very viable large scale storage option. So we also try to look at other alternative options like redox flow batteries. I have some work going on vanadium as well as all iron flow batteries, work on kinetic and transport models and durability studies and so on. So this is a brief of what I do in terms of so apart from this, the other part is what I'll be presenting is on fuel cells. So this is, again, we do it for a space research organization. This is a battery degradation models. Just like batteries, we are also working on proton exchange membrane fuel cells, trying to integrate more physics and make a more comprehensive model. And finally, this is the experimental part that I work on, which is recycling of used batteries. So we are currently trying to implement both hydro and pyrometallurgical techniques to come up with how to extract valuable metals or materials from used batteries. So that is something that we are working on. So these are just to give you an overview of my research area. Just All right. All right. So just to give you some brief overview of the degradation models we work on, we try to combine both physics, mechanical degradation as well as chemical degradation to understand how degradation progresses in a lithium ion battery, both through stress generation as well as SEI and other phenomena. And that is one part of the work. Then we also have, sorry, there's some lag in what I'm trying to present. And the other work is on building models for sodium ion batteries. We have a collaborator who is working on materials for sodium based batteries. We are trying to again assess performance as well as predict life and degradation in sodium ion batteries. So these are some research that happens. I also work on certain non-electrochemical related aspects, which I have omitted for this particular audience, but this is more on long-term energy models, energy security, and energy scenarios. But so this is just a brief overview of what I work on. So now that I've kind of set the stage of my background and research interests, I'll now move on to two specific topics. Like I said before, the first one will be on the system integration, which will be on battery modeling and system integration. And the second part would be on the fuel cell. So to start with, so there are, again, a lot of people would have seen this slide. I'm just continuing this again. So we have different types of battery models that you have available, depending on what you want to achieve, starting from very simple circuit-based models to complex DFT molecular dynamic models. So depending on what you want to achieve, how much time you have and stuff, you end up using whatever model is suitable for you. So the one on the far left here is basically the equivalent circuit models that are quite fast, simple, easy to understand, very easy to implement. And however, they are unable to provide any knowledge on the electrochemical characteristics of batteries. And this is what is predominantly used in most of the systems as of date, but it's not very, it's unable to provide you what is really happening inside the battery. So that is why we try to move to physics-based models. Basically, you get insights into physiochemical processes and also on concentration, potential distributions, current distributions, and so on within the sandwich. It also provides us or insights on thermal analysis, what happens due to thermal variation, along with other degradation mechanisms. The only drawback or issue is these are coupled partial differential equations, so it is very difficult to set up and simulate these models on a whim, unlike those circuit-based models. So there is a significant effort involved in solving these models, simplifying them, and trying to make them cater to needs of battery management systems and so on. So those are the difficulties that are available. So the motivation here in terms of system integration I talked about is when you are trying to build these microgrids. Whatever study I'm presenting is something called as a microgrid. Just to explain what a microgrid is, you have a islanded or a secluded system, like you have a town or a city that needs to be completely energized using renewable sources. So there is no external grid or electricity being provided. I'm just trying to study the demand pattern of whatever energy they need and provide it using renewable sources, like either a solar PV panels or wind systems. So in this cases, what happens is oftentimes when you have these batteries, the life of the battery is not really taken into account. And when you are sizing these batteries, you don't put in much of an effort to understand how the battery degradation takes place. Or oftentimes when you look at the nameplate ratings, as you call it, or the spec sheet of a battery, the battery just says, okay, this battery would last for these many cycles at this temperature, but all these test data are based on lab level testing. So you don't really know if I put it in Austin, my daily temperature is more than 100 during summers. I mean, the battery performance is going to take a hit. And if I move up north during winters, it's going to be, I mean, somewhere close to probably even in the tens. So then how am I going to address these effects without considering them? And if I design a battery assuming which is all these conditions are not being taken into account, so I end up with a lot of unnecessary expenses as well as surprises when the system doesn't work properly. So there is also a lack of robust control strategy on how these batteries are operated. And like I said, oftentimes the control systems in these don't use physics-based models, which is another reason why you don't have control over what you can. So what we tried to do is we tried to find the impact of operating conditions, temperature, as well as the capacity fade on these long-term simulations, long-term, like let's say what happens if I do it for over a year, what happens to the system? And oftentimes the way we test in our labs include constant charge and discharges that are in a well-controlled environment. So that doesn't happen in the real life. So how does it affect the battery? So these are the motivations. So ideally, the work tried to bridge the gap between battery models, which is building at a micro scale, to a system level analysis of what happens to the entire system depending on what happens inside the battery. And this is basically to identify and resolve the inconsistencies in our understanding as well as to give inputs on how better the system can be designed. So to start with, we took a degradation-enabled physics-based model. Again, this is again just a framework. You could mix and match with any type of model, any type of degradation mechanism. Just as a proof of concept, we assume the degradation happens only due to a SEI layer buildup. So that was the only degradation mechanism considered. We built a P2D, the pseudo two-dimensional model that is the most commonly used battery model used, and tried to integrate it into a system that is also, we also had the irreversible capacity due to lithium loss as well as active material loss. And the first work that we did was basically to understand the control logic, how this works. So oftentimes what happens is when you're having, let's say, just a solar panel connected to a battery, how do you operate the solar panels? So there is something called MPPT, which is maximum power point tracking, which basically makes sure that your solar panel is always operated in such a way that it provides the maximum power. Okay, so, but if I don't need that much power, so I'm generating, but I don't have a need for it, then what happens? Usually all these systems come with something called as a dump load. So this is just a huge resistor load box that just eats away all the excess generated power. So the first goal was to avoid this dump load, to change this maximum power point tracking in such a way that it produces only as much energy as we need. So if I have, let's say I have to light this auditorium and I also have a battery, if my battery is not charged, any excess power produced will go in charging the battery. And once that is done, then whatever excess power is there, it has to be dumped. This is the conventional scenario. What we try to do is we don't generate that much power. We generate only as much as needed to light this auditorium and charge my battery. And if my battery is charged, the power produced will automatically reduce based on the MPPT algorithm that we have. So you will only generate what is needed. This kind of alleviates the necessity for having a dump load in your system. So that was the first thing we did. The next part, so like I said, it either operates in these two modes, which is the MPPT mode, which is basically trying to make sure it is always the maximum power, or the power given here is always constant. So these are two modes that we operated, and then tried to mimic the system to be operational for a small city or a village in India by getting their real data along with their real solar installation. So this is what we try to do. And what we can observe is we can also look at, since we have a physics-based battery model integrated, we could understand what is happening inside the battery during this operation. And that helped us to see how the state of charge is varying over the year. So you can see this is a specific days, like day 172 to 175. Ideally, we did it from day 1 to day 365 is like Jan to December. So this is at some certain level, you can see how much the SOC is varying, as well as how much the battery power that is being drawn or given to the battery changes. So this is where we started in terms of having a robust control strategy to operate the system. Then we moved on to having a temperature control. So obviously we know that there needs to be a thermal management system. If your battery is not properly in an air conditioned place, you are going to have degradation and losses because of that. So the idea here is trying to see if not adding any additional control, any additional cost. All we did was we just stopped charging the battery if the temperature was above a certain. So just by doing that, we could actually minimize the amount of capacity fade over a year. So basically, we know that while charging, discharge is something we cannot control because that is governed by the usage, but the charging of the battery can be controlled by us. So what we did, we just stopped charging when the battery temperature is beyond a certain number. So in that case, what happens? The battery doesn't get fully charged always, but we were able to maintain in such a way that you can see this graph on the right here that basically says how the capacity fade happens. If we had just a temperature control, the charging was cut off if the temperature dropped, moved above 40 degrees Celsius or moved above 38 degrees Celsius. We couldn't get to any lower temperature because the system wouldn't survive, because the ambient itself is 35, 37. You cannot have it anywhere below that. But as you can see, there is a significant amount of saved in terms of losses or in terms of capacity fade by just controlling the temperature. The drawback or the issue with this is, you can see that when we do a temperature control, I'm stopping the battery from charging, essentially meaning I'm having to operate the battery at a higher SOC window. So if the battery originally operated somewhere between 60 to 100% SOC, in a case where I had the very strict temperature control, my battery had gone down to close to 10% SOC. This in turn also affects your battery life. You are always advised to operate it between as low SOC window as possible to prolong its life. So that's so that enabled us, gave an idea to figure out how to optimally size this battery, considering the SOC window as well with the degradation. So that was the next part we did. Again, the first two things I told was only for a solar panel and a battery combination. Then we tried to see if we can take wind also into the mix, because just solar alone wouldn't be enough. So we went for a hybrid configuration where we looked at these are all real life data. You get a load from the community, you get the temperature, solar irradiation, and wind speed. All these are publicly available data. Then you look at system sizing. We have our own power management and control strategy on how to charge the battery. And we also looked at what is the economic feasibilities of having a larger battery or smaller battery. How would it affect the performance or the cost in terms of the sizing of the battery. So this is what we did. So for this, again, this is the different locations in India. Again, it's not a one size fits all for everything. So you have to actually make it for each location. For example, if you just look at, we took about 3 different locations, one in the west coast, one in the central part, and one in the southern part, depending on the type of the location, because the solar radiation, wind speeds are all different in these regions. You can see that for the same battery at different location, the useful life or the degradation changes differently. And just to meet their demand, the size of the battery was also slightly different. It was not the same battery everywhere, but you can see that because of the location, the life changes. So that also has to be taken into account when you're trying to size it. So this is, so what we did was we tried to do economic feasibility, and again, based on a yearly degradation, which can be extrapolated to whatever you finally want. So the idea is to study the size, degradation, as well as cost interdependency. So to start with, we look at again a detailed physics-based model and integrate it with a solar wind microgrid, which would then enable us to understand what would be the optimum battery size that would be needed for a given load profile, and the effect on degradation because of either a smaller or a larger battery than what is required. So the idea of operating the battery at an optimal SOC range, basically if I have a battery that is twice as large as what I need, the life will be longer because I'm not going to be using more than 50% of the battery, right? So is there a, but what I'm spending twice the cost upfront, but am I gaining anything by doing that? So is there a sweet spot that I can hit where I still get the benefit of using a lower SOC window, but still, I mean, not spending more on the battery? So that's the kind of analysis we did. And to start with, then we also looked at different cases or combinations of wind and solar. So how do I, so if I want to design a microgrid, so what percent of it would be solar, what percent of it is wind, and depending on the location, that would also vary. So a place may have a higher solar potential, but very poor wind potential. Then there is no point in having a wind turbine erected there, and so on. So we tried this for a specific city again, as I showed in the map earlier. And we used, I think the 70% solar and 30% wind is what we used for our studies that I'm presenting now. But as you can see that the SOC range varies depending on for these three different regions, and this will give you the capacity loss at different places just by operating the battery of different sizes. Again, the size requirement is completely based on their local needs, the size of the city, as well as their solar insolation and wind data. So from this, what we tried to figure out is we tried to understand what would be the operating SOC window over a year for these batteries at different sizes. So my base case is actually what is actually needed to meet the system demand. So that I call it 100%. Then I try to vary the size of the battery by, I reduced it by 5% and also increased it in intervals of 10% to see if there is a sweet spot. If I invest more on the battery cost, would I still be able to make some profit in economically? So as you can see, what we figured out is this is how the degradation here per year, as you know, as you increase the size of the battery, obviously the degradation will decrease because I'm not using half of my battery. But when you come to the cost per unit, this is in terms of rupees per kilowatt hour, you can see that it initially raises, but there is a fall after a certain place, and then it again rises back because you are not making any monetary benefit by increasing the size of the battery. And this is for a certain years of operation. So based on that, we were able to get that you can come to a sweet spot, which is still using a larger battery, but still making economic sense to use. So this is something that we did. So just to summarize, this is just to give you, and again, the analysis that went behind is on how the thermal variation happens inside the battery. I mean, how to control ambient temperature. So if you are, again, all these are without adding of additional equipment in terms of thermal management or any other additional power electronics. With an existing system, how easily to make sure that there is a better performance of the battery. So that was the idea for this work. So this kind of concludes my first part of the talk. I can just break for a minute or two if there are any questions, or I can continue before I move on to fuel cells. Yes.
So the size of the battery in the graph on the top left. So the 150%, I think that means that it's like 50% more than the required base capacity.
Right.
So why is the SOC range for that more on the lower side? I thought it would be more on the higher side.
No, it is the window of SOC being used.
Oh,
It is the SOC window. So 10 to 40% is the gray, and if the battery SOC window is 40 to 70%, it's an orange. So the gray has, I mean, if you put thrice the size, it will be fully gray. I mean, the gray is the one that increases. You are not using that ideally. Yes.
How well understood are the degradation mechanisms and in particular, like, do they change with the scale of the batteries? Because like you already mentioned about these things that are tested at large scale settings. So is the degradation large?
Yes, that's a good question. Nobody still understands how much. I mean, that was my first slide. I did not go into that. I'll just, the very first slide I presented. The top left here. These are all possible degradation mechanisms. Many are still not accounted for. So the issue is we don't know which one is primary. There would also be cumulative effect. So it's difficult to identify. But what we do try to understand from our models is there are parameters that we know are getting affected over time. So we could track them and say it is due to a transport limitation or a kinetic limitation, but it is still not that easy to predict. This is the mechanism that happens. But your question on scale, the scale it doesn't really affect because the single repeating unit is of the same size that you test in lab. Because you don't have a large battery, you just make, let's say, a 10 ampere hour, 20 ampere hour battery, and then just there are multiple repeating units. So that way, whatever lab studies you have done would primarily be good enough to understand what happens at each battery. Again, the environmental conditions and the way it gets operated, that's what is more difficult to do in that. For example, even for your phone, I don't know, I mean, on a typical day, how do you operate? It's not like you always just attend a call at a specific time and then shut it off, right? I mean, it goes on. So that kind of a variable usage is difficult to model, or even in a vehicle. So those are the things, I mean, unless you do some form of a repeated simulation to understand how the battery is behaving, that is what.
Yeah.
All right. Now I'll slightly switch gears. I'll maybe take another 10-15 minutes and then wrap it up. So this part is going to be on the degradation of fuel cells. So again, start with PEM fuel cell is proton exchange membrane fuel cell. So basically trying to convert hydrogen and oxygen to water and directly releasing energy. So why it is good? It does a direct conversion from hydrogen to electricity. It has a higher efficiency compared to any other process how you can get energy from hydrogen. And less moving parts, there are no emissions, your product is going to be heat and water. And of course, there are a very wide range of applicabilities on where you can put these. So, like I said, this is again, you have I'll explain about the operation in a bit. So the basic reaction is hydrogen and oxygen combining to form water. So what we were working on, there are two major consumers. If you look at, one is on space applications. So in case of deep space missions, they require a 500 to 1000 watt-hour per kilogram kind of a energy density, and they also can sustain a large number of cycles because the degradation is not as bad as it is in batteries. The other part is in transportation. Again, long distance travel, operating temperature and weight reduction are all the major issues or areas where they are helpful. And as you can see, the specific energy here in terms of a fuel cell compared to batteries, because this is more of how much fuel you have, it will keep providing you energy rather than battery. You need to look at recharging. So that's the advantage of, and yes, we did have fuel cell based cars and buses that still run. So we don't know what is going to happen, but that's the part of it. So our work here was specifically for space applications. This was for the Indian Space Research Organization, and we are trying to figure out how to get that done. So major challenges here. So this is how your a fuel cell electrode, or what we call as a membrane electrode assembly, looks like. So you have a plate here, and this has these flow channels. So hydrogen is fed through the anode, and you have oxygen here through the cathode. And these are other parts. One is called a gas diffusion layer, abbreviated as GDL. Then you have the catalyst layer, and finally the proton exchange membrane. And the same thing repeats on the other side. So your hydrogen comes through here, it reacts at the catalyst layer membrane, becomes protons, then move on the other side, combine with oxygen to form water. So this is what a basic operation of fuel cell is. So the idea here is there are a few challenges that we are trying to address. The first part is, since water is formed, there is always an issue of water flooding inside these fuel cells. The other thing is degradation, and third is something called as a catastrophic failure when the fuel cell just stops working. So just some math part of it. This is how we have modeled. I will not go into much detail. So this is our cathode outlet and inlet. These are your, just assume the one that I showed vertically is just now put one on top of the other. So this is the picture, and we are trying to solve for various things inside this to understand how the degradation happens, how the species interact, and so on. So the idea here was to develop an experimentally validated three-dimensional model that is non-isothermal as well as physics-based. One advantage of fuel cell operations is once, except for start and stop, during the operation, it's mostly a steady state operation. So as long as you are providing the fuel, which is hydrogen, at a steady rate, there is nothing that changes. It keeps producing your current at whatever rate or voltage that you want to fix. So it is a steady state operation. So mathematically, it makes life a lot easier. And so what we do is we try to analyze the effect of liquid water flooding on the mass transport limitations, as well as evaluate the membrane water content and ionic conductivity at different cell potentials, how they change at different potentials. Again, the idea here is you can operate the fuel cell at varied potentials depending on your application. So the current value will automatically change. And also some flow problem, we try to understand how the outlet, the different flow configurations in the channel I showed earlier, how does it affect in terms of species distribution as well as other aspects inside the fuel cell. So some assumptions here. So we assume that it's a laminar flow, it's a steady state operation, and assume that the gases are ideal gas. And there are also some crossovers that happen which are undesirable, but for this study, we have neglected them. And if you look at, so these are some of the parameters that I'm going to skip. I'm not going to talk about them. And obviously, I'm not going to spend time on all the equations at this point. I'll briefly mention what the idea is and then move on to the results. So as you can see, these are you have mass, momentum, and charge conservation that are being accounted for inside the fuel cell. So the mass conservation is quite simple. Momentum conservation is important here because you have a flow happening inside. which is absent in battery models. And of course, for species transport and charge conservation, we have these Ohm's law and modified Ohm's law equations. Apart from these, we have to account for the porosities, diffusivities, as well as other membrane conductivities that are provided by additional relationships. So the idea again here is you can usual simple models of fuel cells are single phase models. They don't assume that there is both a gas and a liquid phase that coexist inside a fuel cell, because after a certain temperature, you have completely one phase. So single phase is what normally used. But since we are trying to do a multi-phase model, we also had to then include a membrane water transport model, which basically talks about how the membrane, so there is water formed inside, how it actually transports it to the out of the fuel cell, and there is also flooding and waterlogging that happens inside depending on the rate at which they are produced. So this is something that we try to model. And if you are interested, I can chat about the equations and how they come later. So basically we use a modified Darcy's law accounting the liquid water flux in the porous media. And then the capillary pressure and saturation pressure are related using this relation. So just to give you an overview of the entire model equations, this is how the model equations look. So I'm just going to, this is a comprehensive slide that talks about the multi-phase model equation. So the first step we did was to validate our model with experiments. So the reason for moving from single phase to multi-phase models was because, as you can see on this slide, the single phase model was actually slightly, the multi-phase model is better in terms of predicting the actual experimental data than the single phase model. So that is the reason why we wanted to move. And the left here is just to understand the mesh independence or grid independence to see which grids, amount of grids that we need to use. So if you look at, again, I'm not going to get too much into the details, just to give you an idea of what kind of analysis we are able to do with these models. The idea here is looking at operating the fuel cell at different temperatures, let's say 40 degrees and 70 degrees, and then understand for different flow configurations, how the mass transport limitation affects the water flooding, and also whether reaction kinetics has an effect on how much of liquid water is produced inside the fuel cell. So this was the rationale behind getting the study done. And as you can see, the power, so you can see that at 40 and 70 degrees Celsius, there is a difference between how much liquid water flooding happens and also how much is generated. And the same is studied for two different flow channel configurations. Again, we tried for several configurations. We narrowed down to these two, which seem to be the better performing configurations. And these two figures actually show the oxygen variation inside the cathode for two different flow channels on how the concentration varies, because you are pumping in oxygen and hydrogen from two ends of this fuel cell. So there is a flow channel. So there is some mass transport limitations that cause the O2 mole fraction also vary, or the distribution of oxygen, which is where the reaction is going to take place. So we could see that in case of a hybrid channel, we could have a uniform O2 distribution and a non-uniform oxygen distribution in a parallel channel. So again, some insights into the results of what happens in terms of different configuration for the mole fraction and with respect to temperature raise. So as you can see, the left here is talking about two different temperatures for a hybrid configuration, and this is the parallel configuration at two different temperatures. You can see that the oxygen mole fraction decreases with temperature raise as the way the distribution of oxygen concentration works. And similarly, this is for the reactant distribution, basically how the temperature heat map is different for different temperatures at different locations inside the panel. Again, the picture you see here is just to give you an idea, it is, sorry. Just to visualize, I'm just going back one more. Yeah, this is what we are looking at. Okay, similarly, I mean, the model is able to give us the membrane water content from how it varies from inlet to outlet. So this is the water produced due to the fuel cell operation and how it changes during, and the overall water content. We could see that it would decrease with increase in temperature. This is the 40 degrees and 70 degree operation. And this is expected and we are able to observe it. Now the point is how to then look at how it affects the ionic conductivity of the membrane. So if there is a lot of water, the ionic conductivity is reduced. So that is also something. So it is both a function of temperature and water content. In case of a hybrid configuration, we were able to see that there were uniform water gradients, which allowed us to, have a better performance of the fuels. So I'll just summarize these results because I think we're running out of time. So we have a multi-phase physics-based model that estimates the LTE's low temperature fuel cells performance with greater accuracy, which is what I showed. We could get a better prediction using a multi-phase model compared to a single phase model. And we were able to get about 10% increase in performance at a higher temperature with a hybrid flow configuration. And also the reason for this was there was a uniform water content inside the membrane, which improves its power output. So this directly affects the performance of your fuel cell. And finally, we did figure out the hybrid configuration for the flow was superior due to uniform reactant as well as liquid water distribution. So what we are currently working on is transient analysis of water flooding inside the gas diffusion layer as well as the catalyst layer under different load profile. So if you change the potential at which the load at which the fuel cell is operating, this is expected to change, and also include membrane swelling and shrinking as well as reason for mechanical degradation. So this is what I had. Just a brief acknowledgement. The guy on the left, both are my PhD students. He is graduated and is now outside, but he was the one who did the system integration work, and Mayur and Akshay is now working on the fuel cell part. I'm thankful to all the support from the funding agencies for both these projects. I'll stop here if you have any questions.
I have a question with the fuel cell part.
Yeah.
So it sounds like you're saying the better performance at high temperature was basically because the membrane was more conductive because it had less water.
Ideally, yes.
I think that's probably why.
That's probably why. Yes, I mean, we were able to also look that, I mean, two things were studied. One is the flow configuration as well as the temperature. But yes, high temperature fuel cells are known to perform better. But are we able to?
Really important thing.
Huh?
Is it because the removal of the water?
Yes, it's quicker.
Was faster in a different flow?
Yes.
So I guess my other point is like, you saw that it was condensing less at high temperature, which makes sense.
Right.
Is that just because the saturation pressure of water was higher?
Yes. Ideally, yes, that is the reason. I mean, it's common sense. We are just trying to mimic it for the fuel cell so that if we change other configurations, we'll be able to see its effect without actually performing the experiment.
You could probably achieve the same thing by just increasing the flow rate at lower temperature.
That would see the flow rate affects what happens to the power of the fuel cell. You have to operate it at a certain rate. Yes, all these factors affect. There are certain parameters that are fixed based on the needs of my application. And I cannot go beyond a certain flow rate. I cannot, and I will waste a lot of fuel if I increase the flow rate.
I guess the basic part of my question is, I assume it's some cost required to make the temperature be higher.
Yes, so we ideally wanted it at a lower temperature. So the question is, can we get it done at a lower temperature without, can we get it done at a lower temperature without sacrificing too much of its performance?
Yeah.
That's the idea.
So did you know like how much cost benefit you get by going to high temperature?
We have not gone into the cost analysis for
Yeah,
this.
yeah.
Like I said, this was for a space research organization. They like don't care about the cost
Yeah,
at this point, but yeah, that would be a good thing to take up this.
I think like especially in.
There are a lot of studies available practically. I mean, we
Yeah,
did not do it.
Everybody focused on the catalyst, but then it's like really just these like device level issues, like
Right.
flow rates and temperature really seems to have
Yes,
almost a bigger impact than the actual application.
true.
Yeah.
Thanks. All right, if there are no other questions, I can maybe we can wrap this.
So yeah, thank you very much. I keep looking for.
Thanks everyone.
Hey, Professor, can you hear me?